Okay, hello everyone. Let us continue our previous lecture. In this lecture, I want to talk about the Faraday's laws of electromagnetic induction. Faraday's law of electromagnetic induction. It is interesting. Okay, so what is Faraday's laws of electromagnetic induction? In our previous lecture, we talked about the Oersted discovery. I said current produced the magnet. Now think reverse way. If current produced the magnet, then is magnet produce the current then? That is about the Faraday's laws of electromagnetic induction. For example, let us suppose you have a coil. This is a coil. Okay, this is a coil. I have a coil here. I can show you like this. You have a coil. There are many turns. This is a coil. There are, I don't know how many turns it has, or 3,400 turns loop. This is a coil. Okay, 3,400 loop. This is a coil. So you can draw like this coil. Okay, and this coil is connected to the galvanometer. This is your galvanometer. Galvanometer is like this. This is the galvanometer. This is the galvanometer. This is wire. So this is the galvanometer. So what is galvanometer? Why do we need this? Galvanometer, it can detect the current in the circuit. If there is any current, then this galvanometer deflect. So galvanometer is used to detect the presence of current in the circuit. Even if you have a very small current, this device can detect the current in the circuit. So galvanometer. We have another one, ammeter. We did that in electricity. Ammeter is the device to measure the current. To measure the current, we use ammeter. There is another one, voltmeter. Device to measure the voltage, potential difference, we use the voltmeter. But today I am going to use galvanometer. Okay, so the black one goes here, ground, and I want to plug this red one here. Now look, there is no deflection, because look, the circuit is not complete, no current, so no deflection here. Now I want to connect this to the coil. Okay, I have a coil here. I want to connect. I don't know if I can. I don't have any assistant here. So I want to 1 second. Okay, I want to connect the galvanometer. I want to make a circuit here. So this is how. Look at this. 1 second. Look, I complete the circuit. I connect the galvanometer. I hope you see this. This is a galvanometer, and this is a loop. I mean coil. Look, I connect this. So the circuit is complete. The circuit is complete. But do you see any deflection? Do you see any deflection on the galvanometer? There is no deflection here. Okay, there is no deflection. I don't know if you see it. So there is no deflection. Now I have a magnet here, and if I bring the magnet here, look carefully, do you see any deflection there? If I move the magnet, I can see the deflection there. Look, I move the magnet and I see the deflection there. The needle is deflecting like this because I move back and forth like this. You can see the deflection. You can see the deflection. Please observe carefully. But if I keep here stationary, okay, let me show you a little bit better way. I want to 1 second. What I want to do is, let me show you right here, so you can see now. the circuit is complete and there is no current in the circuit. That is why you don't see the deflection. You see this is a coil, and here you have a galvanometer, no deflection. You see the needle is at 0. Now if I move the magnet, now look, you can see the deflection. Look, you can see the deflection. I am moving the magnet near the coil. You can see the deflection. I can see the deflection. What does this mean? If you see the deflection in galvanometer, that means there is a current in the circuit. Right now there is no current, but if I move the magnet, look, if I move the magnet, then the current produced there. If I keep this magnet, look here, if I move, you see the deflection. That if I keep there at rest, no motion, no current. If I move, you see the deflection. Look, if I move, you see the deflection. But if I keep it at rest, no current. Just if you keep at rest, it is look, at rest, no motion, no current. Move, there is a deflection. If you move, look at the direction of the needle. If I move down to the left, if I move away to the right, the direction is changing. Okay, so what does this mean? We'll talk about it. Or if I, other way, like look here, I want to keep the magnet there, the magnet is at rest. Now if you move the coil, you don't have to move the magnet, you can move the coil also. If you move the coil, look at this, I'll move the, it is difficult for me. If I move the coil, you can see the deflection. Look, I am moving the coil and you can see the deflection. So either you move the magnet, or you move the coil, you can see the current there. So what happened, I'll explain that. Okay, so this is the Faraday's experiment. So what is it? We'll talk about it. That is one demo, and another demo is I'll show you in a few minutes, after a few minutes. Okay, so let us talk about this. Here, this is the coil, this is the galvanometer, no deflection, no current. So here, this is a magnet. If you move the magnet down, or if you move the magnet like this, up and down, you see the deflection here. If you move down, the deflection is in one direction. If you move away, up, the deflection is another direction. But if you keep it at rest, the magnet is close to the coil, but it is not moving, no current. That means if you do not move the magnet, we say that the magnetic field is stationary, constant magnetic field, no change in magnetic field. So you have a magnetic lines of force like this, this is your magnetic lines of force. You must have a changing magnetic lines of force link with the coil. That means the magnetic field link with the coil must be changing magnetic field. So current produce the magnet, but don't say magnet produce the current. You have to say the changing magnetic field produce the current. The changing magnetic field, changing magnetic field produced the current. So what does this mean? If you move the magnet up and down, that means the magnetic flux link with the coil is changed. Okay, so the rate of change of magnetic flux induced the electromotive force here in the coil. If you move the magnet up and down, or if you change the magnetic flux link with the coil, the changing magnetic flux that produce the electromotive force, EMF, where? Here in the coil. And if there is a electromotive force is simply like a potential difference. So if you can maintain the potential difference between the two terminals, then if the circuit is closed circuit, then current flow through the circuit. So if you move the magnet up and down, you induce the EMF in the coil and that induced EMF is responsible for the current in the circuit. So using the changing magnetic field, you induce the EMF in the coil, and that induced EMF E, the induced EMF E, this is proportional to the time variation of magnetic flux, delta phi over delta T. This delta phi over delta T, that is the rate of change of magnetic flux, or simply you can say if you change the magnetic flux, that changes the magnetic field. So simply the changing magnetic field produce the EMF, electromotive force, potential difference. And that electromotive force, if you are able to produce the electromotive force, and if your circuit is complete, then the current flow through the circuit. So the EMF induced in the coil is directly proportional to the rate of change of magnetic flux. Or you can say that the time variation of magnetic flux gives you the induced EMF. The time variation of magnetic flux gives you the induced EMF. Okay, so here the induced EMF is proportional to the rate of change of magnetic flux. That is why if you move the magnet fast, quickly, you produce the bigger current there. If you do it very slowly, then little small current there. And this equal, you can write down N delta phi divided by delta T and put the negative sign. Okay, so what is N? N is the number of loop, number of turns. N is the, here in this equation, EMF equal to negative N delta phi over delta T. Here N, this is number of turns, loop. How many loops you have in the coil? Number of turns. N is the number of turns. So if you have only one loop, just one ring, one turn, in that case, if N equal to 1, you can also write down E equal to negative delta phi divided by delta T. Now the concern here is, why negative sign then? Why negative sign? Now look at this. If you from here, if you move the magnet down like this, if you just release, if you release from here, the current produced, don't you think current, it is form of energy? Don't you think you are creating the energy here? If you simply drop this like this, don't you think you create the energy? Is that possible? Can we create the energy? No. We know the conservation of energy. Energy is neither created nor destroyed, but you can transform from one form to another form. So what happens is, if you have a kind of big, long coil having many turns, and if you have a strong magnet like this, let us suppose you have a coil kind of long having many turns, and if you have this magnet is really weak magnet, if you have a strong magnet, and if you drop, it cannot pass through the coil easily. You have to push hard. If you want to move the magnet down, you have to push hard. That means you have to do the work. Then in that case, your energy is converted into the electrical energy. Okay, so what happens is, if you move this, look here, what happened, look here carefully. If I move this magnet down, the electromotive force is developed here in the coil. So that electromotive force produces the current. And I told you, current produces the magnet. So here, moving this magnet, I induced the current in the coil, and that induced current produced the another magnet here. Everyone, this is my source magnet, external magnet. And by moving this magnet, I create the current here in the coil. And that induced current produced the induced magnet, another magnet, new magnet. One magnet here, another magnet is our source magnet. So what happens is, the induced magnet here opposes the motion of the source magnet. The induced magnet opposes the motion of the source magnet. So if I want to move downward, the magnet here, the induced magnet here, restrict to move this down. There is another magnet here, we call induced magnet. This induced magnet opposes the motion of this source magnet. So if I want to move down, north pole develop here, and this north pole and this north pole, they repel. So it is very difficult for me to move it down. If I want to move this away, so if I want to move the magnet away, so south pole develop here, and this north pole and the south pole attract. So I want to move away, but the north pole attract that. So the induced magnet opposes the motion of the source magnet, external magnet. The induced magnet opposes the motion of the source magnet. That is why, to indicate that, I put the negative sign. And this is the Lenz's law. This is the, we call Lenz's law. What is Lenz's law? Lenz's law simply gives you the direction of the induced magnet. The induced magnet always opposes the motion of the source magnet. That is why you put the negative sign here or there. You can see that. Look here. I have one tube. This is copper tube. This is copper tube. Okay, copper tube open, both end open, copper tube. And I have two objects. Look, two objects. This object and another object. They are identical. They are identical. One is magnet, other one is simple the regular object. One is magnet, other one is simple regular object. I don't know which is magnet. I don't know which is magnet. Look, they look identical. So what do you think? Which is magnet, which is not a magnet? Let us see what happened. What I do is, you observe carefully, okay? I release this object. I don't know if it is a magnet. I release this. I drop this from here, from the hole. And please observe carefully how long it takes to come out from this end. I drop from here and measure the time how long it takes to come from here, from other end. If you have a timer, you can try that. Let me see. I drop from here. Quickly, maybe less than a second, quickly. So again, look here, everyone. I drop this from here, quickly, almost like even less than a second. Now let us do the other one. I have a different one. This is different one. Now I do the same thing. I drop from here and measure the time. What happened? If it is again a second or less than a second, look at this. Okay, 1, 2, 3, go. Look, it is. Again, look at this. Measure the time. In the previous case, it was less than a second. Now, 1, 2, 3, go. Look. It takes a long time. Again, look. It takes a long time. What happened? So from this experiment, I can say that this is magnet. The other one is not a magnet. The other one, that is not a magnet. But this is a magnet. Why? Because when I drop this here, this is a copper. So when I drop this magnet, so if I move, if it is moving down, the magnetic field is created in here, right there. Because when I move it down, the magnetic field link with the player, this tube is changed, and that creates the induced magnetic field there. That induced magnetic field opposes the motion of this. Okay. Other way, we have to talk about it is better to know the eddy current. Okay, I don't think so we have to go over this. So what happens is when I move it, okay, so the magnetic field link with this tube is changed, and due to that changing magnetic field, EMF induced here, that EMF, the induced EMF, due to that induced EMF, the current is flowing there inside the because this is a copper has a free electron, and those electrons are moving. The motion of the electron, that is called as the eddy current. Okay, that is called as the eddy current. Okay, and that current, of course, produce the induced magnet again. You know that, right? And that is why the motion is it takes so long. It's so long. Look, it's so long. Okay, so when I move it down, the magnetic field link with this tube is changed. That changing magnetic field creates the current. That is the eddy current. Okay, that eddy current produces another magnet, the new magnet, induced magnet, and due to that, the induced magnet, this magnet repels this magnet. That is why it takes so long. That's why it takes so long to come out from other end. So that's why if it takes a long time, then from this experiment I can confirm that this is a magnet. The other one, that is not the magnet. that is this one. This one, look at this. If I drop this, look here, I can do together. Look, this one, quickly. Other one, this is the magnet. Look, it takes long time. Look, it takes, so this is the magnet. This one, this is not the magnet. So the rate of change of magnetic flux, that gives you the EMF, induced EMF. Okay, and this induced EMF, that is proportional to the time variation of magnetic flux, and that is a Faraday's laws of electromagnetic induction. So simply the the hydropower dam, that based on the Faraday's laws of electromagnetic induction. So simply the water is moving there. Actually the kinetic energy of the moving water, that is converted into the first rotational kinetic energy, because you have to rotate the turbine there. If you rotate the turbine, then the turbine is in between two big magnetic pole there. So the magnetic field linked with the turbine is like a coil, change, and the EMF induced there. You can do this here also. Let me show you. Without using battery, without using any source also, we can produce the electricity. Look at this. I have another demo here. Here I have one setup. This one. I hope this will work. There is a light bulb. These are the magnet. Okay, and there is a coil inside there, but there is no source of the electricity there. So if I change the magnetic flux link with the coil is inside there. So what I have to do is I have to rotate this. You see there is a handle right here. I have to rotate this. What happens in hydropower is simply to rotate this handle you use the water. Okay, so I want to rotate myself here, and I will see if I can produce the current. If the current is produced, then you can see the light bulb there. You see the light there if current produced. But of course, this magnet is not a strong magnet, and the coil has not too many loops, so I don't think I can produce the large current here. But let us try. But since the room is light bright right now, I want to turn off the light. Okay, just give me a second. So what will happen, you can see. Okay, okay, so please observe carefully. There is no light. You can see the light bulb. Now I want to rotate this handle. So 1 second. It is difficult for me, guys. I am alone here. I don't have any assistant, so I don't know if I can show you. Let me try. It is really hard for me. Observe carefully the light bulb. If you see the light, yeah, I see it. You see the light there? It is really dim, but I see that. Okay. So what happened? You see the light. It is dim, but I see that. I hope you guys also see that. Okay. So what happened there is my energy is converted into the electrical energy first, and then the electrical energy is converted into the light energy. So that is what happened there. Okay. So here, this one I showed you. What happened is, look, there is no battery, nowhere. Okay, no battery. I have a magnet and I have a coil inside there. Okay, that's it. No source of electricity here. But I rotate this, and you see that the light produced there. Actually, what happened? First, by rotating this, I changed the magnetic field link with the coil. Coil is inside there. I changed the magnetic field link with the coil. That changing magnetic field produced the current, and due to that current, the light bulb, you see the light there. So this is the Faraday's laws of electromagnetic induction. Okay, this is the Faraday's laws of electromagnetic induction. So please keep in mind the rate of change of magnetic flux that produces the EMF. Okay, that is directly proportional to the EMF. Okay, and here the negative sign indicates that the induced EMF that induced the magnet, and that induced magnet opposes the motion of the source magnet. That is the Lenz's law. Okay, so this is about the Faraday's laws of electromagnetic induction. And look at this formula. EMF is N is the number of turns, delta T divided by delta T. So if you want to increase the EMF, electromotive force, If you want to increase this, of course you have to increase the number of turns. That means big coil having many turns. If you increase the N, your EMF increase. Or if you increase delta phi over delta T, rate of change of magnetic force, you rotate quickly. In that case also, you produce the more electromotive force. More electromotive force means current is big. Okay, so this is about the Faraday's laws of electromagnetic induction. These things, the Faraday's laws of electromagnetic induction, you can use this in many places. Okay, so this is all about the magnetism, Faraday's laws of electromagnetic induction. And if you want to learn more, I will also post the PowerPoint. Okay, so you can read that. But normally your test, quiz, homework is based on my lecture. But if you want to know more, please read the textbook. You can also read the PowerPoint. I will post that too. Okay, thank you.